All right, hello, my absolute favorite people in the whole world. It is Wednesday, April 29th, 2020. We are on our last day of the dynamics unit before we move into uniform circular motion and gravitation. I'm going to break it up with we on to a sustainability day? Yeah, breaking it up with a sustainability day in there. As we move further into this fourth quarter and that much closer to the end of the school year. Just to review, we hit almost all of these objectives with the exception of fields and carriers, fundamental forces, and then we got to do some more Newton's third with deformation scenarios. We defined force on a basic level, talked about its vector properties. We talked about, we built on our understanding of reference frames and how it pertained in situations where our inertia gives us the indication that there might be a force in play. We will build on that more next week when we start getting into circular motion. We talked about Newton's first on like the most basic level, and then built on it for it to be more of kind of a philosophical understanding of kind of cause and effect that allows for the rest of physics to kind of blossom out of it. Now we've got Newton's second, which described our different direct and inverse relationships that are available because of Newton's second to define force, mass, and acceleration. We talked about Newton's third. We went over some direct application of it with thrust, normal forces, friction. We did some practice problems with friction. Then tension as well, and then I think we left off at after drag force and a little bit on terminal velocity. I want to start today before we get into deformation, just breaking down kind of the incline plane. We won't turn it into a problem until we get to the analysis portion for this chapter, but we will at least just kind of set it up so that we kind of see the relationships. Now that we have an understanding of friction and constant acceleration on like of an object in contact with a surface and things like that, it should be a little easier because we're basically just adding a little bit more math to it. So before we even get into deformation, let's head to the document cam real quick. So you'll get incline plane problems. It's like after projectile motion, it's the next major like cliche hurdle in physics education. Okay, so you get a problem of theta degree incline, or theta pi radian incline. And you'll have an object that sits on it. Okay. The problem will ask for a number of things. It'll ask you to find the coefficients of friction. It'll ask for you to find what angle makes this object start to slide down, given other information. It'll ask, maybe give you enough pieces to find the actual mass of it. All kinds of different things can be pulled from this incline plane problem because it's like one of the most simple machines to move something, to create an incline. Basically is using gravity to your advantage to accelerate something. So I just want to kind of break it down and define things a little bit. So, and I'll do that by way of a free body diagram. So the force everyone can quickly say that acts on this object is gravity. Okay, Fg. It's weight, and it always acts straight down. The first mistake from the kids who are really into the dynamics portion of the class that they make in these diagrams is typically where they put the normal force. So when we did, like a book on a table, the normal force was always the exact opposite direction of gravity because it's oftentimes so commonly paired with gravity. And it is to an extent, but our normal force is always in the direction that's perpendicular to the surface that it's in contact with. So our block here is in contact with the plane. In this plane, perpendicular would be this way. So the normal force is actually this way. F sub n. Okay? There's a few other things that are in play. What's keeping it from sliding down? Friction. And the one that's keeping it from sliding down is more specifically static friction. Alright? So this would be complete. This would be all the forces acting on it. Which is perplexing because you say, well, if these are the forces acting on it, what makes it move this way? There's no force or anything or any acceleration in the same direction as the plane. So how can it ever be accelerating in that direction or have a velocity in that direction without any forces acting that way? Well, we need to break our gravity into components. Okay, so you really can't go much further without establishing a reference frame. I like to kind of visualize the reference frame as being theta degrees turned clockwise or counterclockwise. So this would be our positive y. This is our positive x. Okay. So really, we've tilted Earth theta degrees to be our actual reference frame, just to make the math a little more, or like the geometry a little more reasonable, or at least for me, it's always been easier to visualize. So that means that gravity isn't like parallel with either of our axes. So it's going to have x and y vector components. FGX, or no, I'm sorry, FGY will be here. So a negative y down the negative y-axis, and then FGX. Sorry, I should have drawn this fully out to here, the length of that arrow. FGX will be in the negative x direction. Okay, and rather than tilting your paper and looking at, or when it's on the board, tilting your head to look at it at theta, having your neck like theta degrees the whole time, I prefer just to draw myself a brand new coordinate plane, put a dot at the origin, which represents the center of mass of the box, and then redraw all these forces right side up, so I don't have to turn my neck. F sub n, FG is now out in quadrant 3, right? And we'll figure out the angles in a second. FGX and friction, static, of course, until it starts moving, and then FGY. Okay, so now we've got everything labeled on a coordinate plane. We need to figure out a way to express either this angle or this angle. So let's look back at what that actually is. So this angle or this angle. Well, we know that this angle combined with theta and a 90 degree gives us like a right triangle here, okay? Which from our understanding of geometry means that this angle has to be equal to this angle, right? Because we've got 180 here, 180 minus this 90 gives us 90, so this angle is technically equal to 90 minus theta, okay? And if you've got a 90 here, this is a 90, so this is technically theta, right? Because 90 minus theta, if this angle is 90 minus theta, that makes this theta, because the whole thing added up is 90. Okay, so anyway, this is theta. And we can start from there. I prefer to go ahead and just draw it. So if you've got your FG, FGY, FGX, we see that FGY is going to be a negative value, FGX is going to be a negative value. Friction is going to act opposite to FGX, and we know that FGX has to be equal and opposite to frictional force, or else we'd see the block start moving this way. So we have these statements when it's at rest that Fx is equal to 0, like the net forces in the x is equal to 0, which would have to be equal to Fgx plus friction. Okay, and from this we can say that they're equal and opposite. Okay, so if we found one, we'd find the other. Frictional force has a formula, so you can plug in the mu s times the normal force, and we'll get to the normal force a little bit more here in a second. And then another way that you can express this, Fgx, from the trig understanding here, we can see that if this is theta from this diagram, this is theta, then Fgx we can describe as Fg sine theta, right? Because we can say sine of this angle is opposite over hypotenuse, or Fgx over Fg and then just move the FG over. Okay, so if you know how much the block is in mass, you take it times 9.8 to get FG, or if they tell you what the weight of the block is, and then if they give you the angle. So this is another statement of FGX. So depending on the information you're given, you can get to all these different things. They're all connected. Now in the Y, we see that the normal force has to be equal and opposite to the Y component of gravity, or else this block would either fall through the incline or levitate off of the incline, depending on which one was stronger. So they have to be equal and opposite. So we could say that all the forces in the Y are also equal to 0. There's no acceleration. A is 0, so F is 0. So that's equal to Fn plus Fgy. Okay, and by the same work, negative Fgy equals Fn. So if you're given any of that information, you can use this relationship. Fn has a relationship with frictional force. So if you're given something about friction, you can move that into the x component, and those can go back and forth with each other. Yeah, so those are about. And then by the trig understanding, you can also say Fgy is equal to Fg cosine theta by the same logic that we made Fgx equal to Fg sine theta. So, so all these different relationships within the inclined plane problems. I'll give you a problem that we have to actually solve for things. I just wanted to introduce it in the meantime. So now let's actually hop into those deformation problems. So deformation is just a change in an object's shape due to forces applied on it. So this is our jumping off point in the 8th grade class. The first big physics concept we learn is pressure. Pressure just being equal to force applied onto a surface area or over a surface area. And we talk about sharpness. We apply it to automobile safety and all kinds of things like that. Deformation is kind of like that concept on steroids a little bit. So deformation can be elastic, meaning after we remove that force or that pressure on a surface, the object will return to its original shape. So Hooke's law will become even more applicable when we get to harmonic motion and like spring-based things. We've already had to use it a little bit, but we see this modeling of a force as it's related to a change in distance or the change in length of something are directly related by way of a linear constant k. So we'll need this for different things. To elaborate a little bit more on this constant k, this is the constant of proportionality. A larger k value means it has a smaller elastic region. It means it's more rigid, less likely to bend. Okay. A smaller k value means this is going to have a flatter slope. Anything less than 1, you're going to see it even like down here. So it's going to have a larger area under the curve and a longer elastic region. Okay, before we get to this area where we've gone past, so like where you think something might be kind of broken, we see some give in the slope on the change in distance here, or the change in length, and then we get to this area where we see exponential increase in length. We've got a permanent deformation here, and eventually reach a point where the object will fracture. Okay. 3 types of deformation we're going to go over today: change in length, sideways shear, and then change in volume, stress, strain, and expansion, shrinking. Yeah. So first one we'll do is change in length. So when you apply a force parallel to the length of an object, so basically either stretching or compressing, to put it in standard terms, we have this relationship. You've got the change in length with this force is equal to 1 over a constant, the Young modulus, and this is something that's just specific to different materials that we found experimentally. So 1 over the constant for that material times the force applied divided by the area. So basically we've got pressure here, force over area, times the original length. a large Y value means it has a large tensile strength, so you're going to see less deformity. We measure in newtons per meter squared. My 8th graders will know that as pressure. So now we see the increase in understanding and complexity of these sort of like civil engineering concepts. Change in length, we can rearrange that formula to where we have force by itself, and then basically you've got Young modulus times the surface area times a ratio of change in length to original length. We call stress the ratio of force over area. So we spent 8th grade and beyond calling that pressure. Now we're going to call it stress. Both are correct. But we can get stress by way of taking the Young modulus times the strain. Strain is a unitless property. We can rearrange it even further. Where we have this, and we see that this still resembles Hooke's law somewhat. We've got change in length. Well, if we just make YA over L naught equal to our constant proportionality, because all these things are unchanging, your original length, the area that the force is applied, and then the type of material, those would create a constant to relate change in length and force. So Hooke's law still is evident even when we break it down this far. Sideways shear. So in situations of sideways shear, this is when we apply the force perpendicular to the length of the object. So like one of those like cheap little shelves in my room, if I apply a force up at the up on this region perpendicular to the shelf, we see that I can't apply enough force to overcome friction between the ground and the shelf. So then the top just starts to move about the stationary bottom. We see a sideways shear, but ultimately just acknowledge that the actual length of the object is perpendicular to the force for it to abide by shear modeling. We call this delta x, the length at which I guess you'd call this the face of it is displaced, is 1 over the shear modulus. It's, again, specific to the material, times our stress, or our F over A, or not our stress, our strain, times the initial length. Okay, all these things go into calculating it. And then the last one, change in volume. So, yeah, like we also refer to this as compression or expansion. This function only works if we can say within reason that force is applied equally on all points on the surface of this three-dimensional object. This is the reason why they don't give us soda bottles filled to the brim. Corking or sealing forces atoms closer together. The negative and negative on the outer shells of the electrons get so close between atoms that it creates this opposing electromagnetic force. And as we change things like temperature, altitude, and things like that, it can lead to explosion, which you don't want. And I'm sure that over time we learned that the hard way, and then found out the science behind it later. But we've modeled this. Like I said, this only works if the force is applied equally on every point of the surface. But the change in volume is equal to 1 over the compression or expansion modulus times the ratio of force to area times the initial volume. Okay. So we've got some opportunity to practice these. Concrete has a height of 5 meters. Has a height of 5 meters. Unit area of 3 meters squared, and it supports mass of 30,000 kilograms. They want stress, strain, and change in height. They want us to say acceleration due to gravity is 10. I'll probably still do 9.8. And then they give us a Young's modulus of 20 times 10 to the 9th newtons per meter squared. Alright, so let's get started. So we're solving for, first thing we do is solve for what the stress is. Okay, so stress measured in newtons per meter squared. So how much stress is this feeling on its surface area because of the force applied to it? So you can get botched up in all those big formulas with the constants and the relationships and all that, or you can think conceptually. This is a slab of concrete, 5 meters high. Surface area of 3 meters squared. We want to put a block on it that's got a mass of 30,000 kilograms. So what stress is it going to feel on its surface when this is in contact is what we're doing here. So just think of that as stress is equal to that gravitational force that it'll feel due to the block on its surface area. So I'm going to go ahead and turn this into positive 9.8. And then we take times the mass of 30,000 kilograms to get the gravitational force on top, A times M, divided by the area, 3. If I want to make my math a little easier, the 3 and the 30, this turns into 10,000. So 9.8 moved over 4 decimal places gives me 9.8 times 10 to the 4th newtons per meter squared. I know it's newtons because I took an acceleration, a meters per second squared, times the mass. So I've got gravitational force in newtons up here, and the 3 was in meters squared. So that's our stress. That's our ratio of force to surface area. Next thing it wants us to do is find strain. Well, I just understand that strain is the relationship of stress over y. So that's just equal to 9.8 times 10 to the 4th for my stress, and the Young modulus was 20 times 10 to the 9th. If I round this to 10, this is 10 divided by 20, so 0.5 times 10 to the negative 5th, because 4 minus 9, or 5 times 10 to the negative 6. And this is, that would be, we took, just to confirm our work here, we took newtons per meter squared, and divided it by a Young modulus, which is also newtons per meter squared. Boom, 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 boom. We get a unitless number, so we know that's probably, we're more confident that that's correct. And the last thing, I imagine they probably want change in height. Okay. So change in height is just going to be delta L. Okay, from our formulas, that just is equal to strain times L naught. Okay, we had the big fancy formula, but if you find stress and then use stress to find strain, and then use strain to find something like the change in length from just the standard formula, just turns into this. So it makes the calculations a lot easier. This was 5 times 10 to the negative 6. And then L naught, our initial position, was what? 5 meters. So 5, we have a unitless number, times something in meters. It's going to give us an answer in meters. 25 times 10 to the negative 6 meters. So very minuscule strain, or change in length, that we were able to find out with just a few numbers. So now we know that putting 30,000 kilograms on concrete of this material that has this specific Young modulus that we found experimentally with this surface area will lead to these results. It'll feel this much pressure, or this much stress we'll have this constant of strain that we can use to find other things, such as a change in length. So we see that actually this concrete was compressed roughly through 10 to the -6 meters. So 10 to the -3 is a millimeter. So a 1,000th of a millimeter. So hardly at all, which is why we're, that's why why civilizations have used concrete for a long time. All right, so then this brings us into some of the more conceptual stuff. We barely touch on this, even in the AP physics course. But basically, we use with our understanding, especially as we get into the universal gravitational force next week, we'll see that forces, and there really is only a few fundamentally, but each of these forces has a specific region that they're felt in. And technically, we'll see next week that I guess one could say technically gravity works over an infinite distance. The region, like for like a Coulomb force or any of these inverse squares, technically an object's gravitational force field exists at an infinite distance. It just becomes infinitely small and pretty quickly negligible, oftentimes. But nonetheless, we're supposed to talk about fields in the AP Physics course. Fields are basically just a region that a force has an influence over. So because I have mass, I actually provide a gravitational field that spans over a very small distance because my mass is so low in comparison to my volume or my radius. But something like Earth that has quite a bunch of mass packed into also a big radius but relatively small radius in comparison to how much stuff is packed into the Earth. That's why it has a gravitational field strong enough to hold satellites and a moon in orbit. Then you move out to something like the Sun that has quite a large mass and also a big radius, but that ratio favors the mass enough to where the Sun holds a solar system's worth of things within its gravitational field. But eventually, if you moved far enough away from the Sun, you would be out of reach of its gravitational field. Electricity and the other two forces that we'll get to in a second also have fields or regions that their influence works over, and that they all decline with distance. But nonetheless, so just kind of this region, and as you learn about magnetic fields versus electric fields and gravitational fields and stuff, you'll see that the orientation and the direction of them are different. But we needed this understanding before we were able to start measuring forces properly and understand why that when we constrained as many variables as we could, why forces were measuring different, why people weighed less at higher altitudes. Came from an understanding of force fields. And then further, to build on that even further, we have carriers. Fields successfully explain the presence or potential for forces to be applied, but we needed like this middleman or this exchange medium for forces to exist. We needed something to carry the information from what is acting on what. We needed a carrier, quite literally a carrier. And different theories have been attempted over the last 100 years to make these carriers like resemble particles and things like that. Most recently, we have the Standard Model, which defines a carrier particle for all four of the fundamental forces. And to better visualize how these carriers would interact between two things, between something providing a force on something else, just as like a repulsive force is felt between two people passing a ball. So the person passing the ball feels almost like a backwards push, and then when the ball gets to the person, even though the ball's coming towards them, they provide a force towards the ball. So just as this interaction occurs, two nucleons would feel a repulsive force as an exchange meson is passed. And this probably creates more questions than answers for you guys, but we will return to this later. But we can't talk about carriers and the current state of carriers without really glancing at the standard model. So you've got your quarks, your up, your down, and then the strange and the charm, and some like the lesser common ones in like nature. And then you've got the neutrinos. You've got the electron, the muon, and the tau. And then we've got our carrier particles. The photon is basically the light particle. The graviton is the one we know the least about. The graviton has only ever been provided theoretically because we need a carrier particle for the exchange of a gravitational force. So, I mean, I would say majority of representations of the standard model probably won't even have the graviton on it, just because it's entirely us creating a particle to explain one of our fundamental forces a little better without having really solid evidence of it. The Higgs boson has been the talk of probably the last 15, 20, 30 years of particle physics. As our colliders got better and we were able to go from painting the negative space around the existence of a Higgs boson to truly detecting it in the last, I think, probably 10 years. And it is within the Higgs field what provides mass to all these other particles. So that is, confirming this had huge ramifications, and also, per usual, striked a lot of new questions. But this is all rooted before in our four fundamental forces. These are the four forces of the universe. Everything else is derivative or like a dressed up version of one of these. So we have gravitational force, appears to be weak, 10 to the negative 38. However, has an infinite range. Like I was saying earlier about when we were discussing fields, gravity. One of the questions that's been on the 9th grade exam over universal gravitation. Each year I ask them to find the gravitational force between themselves and the President of the United States or something, and then compare that ratio to the electromagnetic force between the two of them. The graviton is a carrier particle, the theoretical one we just discussed. The photon is a carrier particle for electromagnetic. The photon's been the particle of probably most study of the last 150 years. Electromagnetic also has an infinite range. How they differ is attractive and repulsive. We see that electromagnetic is stronger. That is relative to the distance and the mass of what we're working with. Gravitational forces are what is largely responsible for things like black holes that not even a photon can escape. So it's relative, and plugging in a few factors, you can figure out pretty quickly the ratio of like how strong certain forces are on things. But we'll get more into that as we get into universal gravitation and Coulomb force. We've got the weak nuclear force, which allows for, from my understanding, which allows for largely like kind of the field of chemistry, or at least what they teach in like high school and early chemistry with radioactive decay and stuff like that. The exchange of these particles here would allow for the weak nuclear force, and then the gluons are what allow for the strong nuclear force. The strong nuclear force is what keeps nuclei together. So inside a nucleus, even as simple as a helium, is two positive charges, and we know that a positive and a positive should repulse each other. And we've got these two positive charges within a nucleus that is 10 to the negative 15th meters wide. So without the strong nuclear force canceling out this repulsion, we would never have a nucleus that would come together. And without a nucleus, we would never have electrons that start to behave atomically. Without electrons behaving atomically, there'd be no baryonic matter. So that's all I got for the dynamics unit. We will continue to return to these. This is basically, if we are chefs, these four forces are kind of like our cutting knives. So they are not going anywhere. So we had these assignments. I'll put videos up to show how to, I'll discuss the reflection in the next video, and I'll put up separate ones for this problem, which has been a question on my AP Physics final, or no, the first question of, or no, not the first question, but on the first test of AP Physics for the last 2 years. I'll do a video completing this, just to go through anything that might have been difficult on that simulator. I'll discuss the deconstruct in the next problem, or the next video, and then we are wrapping up the very first lesson we did with the discuss. We'll have an evaluate. I'll go through and read these and respond to some of these. Okay. Additional resources, I keep adding some throughout the week, so be sure to check these out. There's a really good one on the 4 fundamental forces that I just added, so look at this and check that video out. Alrighty, so long, farewell.